Boa tarde, pessoal. Obrigado por estarem presentes aqui, né, para mais um webinar da SPWLA Brasil. Hoje nós temos aqui a presença do Ole Wennberg. Ele vai apresentar o trabalho The Characteristics of Natural Open Fractures in Acoustic Borehole Image Logs from the Pré-sal Barra Velha Formation. Um trabalho realizado na Bacia de Santos, aqui no Brasil. A apresentação vai ser feita em inglês, né? O Ole, ele trabalha na Equinor já há 25 anos, na maior parte no setor de pesquisa da companhia. Ele atua no centro de pesquisa em Bergen, lá na Noruega, né? E vem trabalhando com a caracterização de reservatórios com foco em ocorrência de fraturas abertas em projetos no Oriente Médio, Norte da África, Noruéga Continental, e até mesmo no pré-sal brasileiro, né? Ele possui mestrado em Geologia Estrutural pela Universidade de Oslo e doutorado em Tectônica pela Universidade de Bergen. Então, novamente, né, agradecer a presença de todos, lembrar que agora nossas reuniões estão sendo realizadas através de streaming no YouTube. A apresentação, nós agradecemos a presença de quem estiver aqui, mas a apresentação também vai ficar disponível aí no nosso canal, e nós incentivamos aqui a participação e que o pessoal faça perguntas no chat aqui, né, para o Ole. Eu vou estar moderando a reunião, então, ao final da apresentação, eu vou ler as perguntas de vocês para ele. E aí, lembrando que para fazer as perguntas, né, vocês precisam se inscrever no nosso canal, e aí já vocês vão ficar por dentro aí dos próximos webinars, né, e também a gente pede para vocês seguirem a página no LinkedIn, onde a gente faz as nossas divulgações, e também de participar como membros da SPWLA Brasil. Não tem custo nenhum, é de graça, basta entrar lá na nossa página no LinkedIn, vocês vão achar o link do Forms para vocês se inscreverem. Então, eu vou trocar agora para inglês, né, e passar a palavra para o Ole. Ole, so we are good to go. You have the word. Thank you again for participating in your webinar. And the floor is yours. You're good to go. moment, we had a technical problem here. Your voice, people are not hearing your voice.
Okay.
Sorry about that. But
Yeah.
people, they told us very trying to see what's happening.
Okay. Yeah.
Just give us a few.
But you
a few
can hear
minutes.
me. You can hear me through Teams. Yeah.
Yeah. I can
But
hear
not,
you in our
yeah.
meeting, but the sound's not going through to YouTube.
Okay.
So just a moment. We'll see what's happening.
Yeah.
Okay, I think we are good to go.
Yeah.
If you could start over again from the beginning.
Yeah, I start with this slide, the introduction. And please tell me if there are some other issues with the presentation or the sound or anything.
Okay.
Yeah,
Thank you.
first, natural open fractures, they are common in carbonates and carbonate reservoirs. This is an example from outcrop it's from limestone in the Middle East, and as we see, it's highly fractured. Natural open fractures have also been reported in pre-salt reservoirs in Brazil, as we see an example of in this image log. The natural open fractures, they contribute to excess permeability, and that is the well test permeability being much higher than the average plug permeability or the petrophysically modeled permeability. These are important to address for dynamic analysis and well planning in addition. The main relevance for Equinor is the development of the Bacalhau field in the Santos Basin and BMC-33 in the Campos Basin, where we also see that fractures are present. And the purpose of this presentation is to show you the characteristics of fractures in pre-salt in the Santos Basin and using acoustic borehole image data, and finally to discuss how they are distributed, their orientation, and what control their occurrence. So then fractures. First, the definition, that's mechanical breaks in rock, representing displacement, discontinuities across surfaces or narrow zones. The first type of fractures, that's the opening mode, that's joints or veins or partly filled fractures. Then we have closing mode fractures, that may be stylolites or compaction bands. Then we have shear mode fractures, that could be faults or shear bands. And both opening mode and shear mode fractures may be open in the surface and act as conduits or high permeability features in these subsurface reservoirs. Fractures have a dramatic effect on fluid flow in some cases. The open fractures, they increase permeability. So a reservoir with poor matrix properties may be produced at economical rates. But the negative side is that they may cause early water or gas breakthrough. So this is CT of a whole core sample illustrating this. The sample was saturated with brine and nitrogen was injected from the right. And then first the gas went through the matrix, but when it did reach a fracture, then you had a very rapid gas breakthrough. And after the gas breakthrough, it was no more brine produced out of this sample. The closed fractures affect on fluid flow. They reduce porosity and permeability. They are typically sealing faults. That's major features, but also baffles or stylolites or deformation bands. So this is an example of a deformation band in a SEM image. It's from a chalk from the Oseberg field in the North Sea. And the porosity is reduced from 30 to 40% in the host rock to about 10% within the deformation band. And this corresponds to a reduction in permeability of about 2 orders of magnitude. Then the challenges with fractured reservoirs. First, the heterogeneity that's caused by fracturing at different scales, and that's superimposed on the earlier heterogeneities, sedimentological and diagenetic products. Typically, it's a large variation in productivity, well rate, tween wells, and also a large part of the production may come from a very short fractured interval within a single well. It's also some challenges related to modeling and simulation. First, to predict the spatial distribution of fractures, and then to quantify multiphase fluid flow, and to represent this in a proper way in field scale simulation model. Often DFN modeling, discrete fraction network modeling, is used for fractured reservoir, as we see an example of this. And it's really important to capture the heterogeneity of the system. So this in black is the single porosity fluid flow simulation, and that's very optimistic compared to when the heterogeneities are included in dual porosity, dual permeability simulation. Then the transfer between the matrix and the fractures, that is challenging to represent. It's typically regarded to be proportional to the matrix block size, the blocks surrounded by fractures, but also diagenetic processes can control this transfer. And then the water gas breakthrough, as mentioned previously, and also mud loss that's frequent in the fractured reservoirs. This is a diagram of fractured reservoirs per lithology, and most fractured reservoirs are in carbonate, in limestone, in dolomite, and also in chalk, as we typically see in the North Sea. So the fractures, they are frequent in carbonate rocks, and a significant part of the carbonate reservoirs are considered to be naturally fractured. And this is largely related to the early cementation and brittle behavior of carbonates. The diagenetic processes, they start shortly after deposition, and they cause the carbonate rocks to be brittle and prone to fracturing at shallow to moderate depths. So then this shows the general fracture concept, and that's how fractures typically occur in carbonate reservoirs, but also in sandstone reservoirs. First, we have the strata-bound fractures. They are within single layers and may stop at the layer boundaries. Then we have non-strata-bound fractures that are not restricted by layering. They cut through a larger part of the strata. And then we have the fault damage zones. That's the fracturing close to faults in that we see in the subsurface. So this is a general concept, and it has been used. It's based on outcrop data, but it has been used in quite a few subsurface studies. Then the geological setting, I don't have to say too much about that. You probably know that much better than me, but we are studying in wells in the Santos Basin offshore Brazil, and this basin was formed during Mesozoic rifting of the South Atlantic, and the main focus of this study is the Barra Velha Formation, which is regarded as post-drift, and this is composed of shrubby limestones and laminated limestones and dolostones, grainstones, and some conglomerates and breccias, and then the spherulitic and dolobitic magnesium-rich silicate clay stones. And the Barra Velha Formation is partly silicified, and that is quite important for the fracture distribution and also the distribution of excess permeability. It is quite a few studies of fractures in pre-salt already. So first, Meneses de Jesus et al. Presented fractures, dissolution enhanced fractures in 2016. Tanaka et al. Related fractures to normal faults and transfer zone. They used DFN modeling and dual porosity simulation to match the historical production. Fernandez Ibanez et al. 2022 described faults and open fractures, connected bugs, and associated these with high flow capacity. Correa et al. 2019 suggested that high well test permeability was caused by high fracture density in carbonate mounts, and it's quite a few other papers that have been published during the last 3-4 years. In the following slides, we will aim to present an overview of the fracture characteristics in the pre-salt lacustrine carbonates in the Barra Velha Formation, and we will also show how the fractures relate to other reservoir parameters and geological features. Then the data, as mentioned previously, this is a study using acoustic borehole image logs. We have studied 19 wells, 17 vertical and 2 was deviated about 30 degrees through the Barra Velha Formation, and about 5,700 meters in total was studied. In general, the data quality is good, and more important, it's consistent so that we can do the statistics in a proper way and compare between wells. Core photos were available in 5 wells, and also petrophysical logs and derived mineral composition. The multimin was used in the analysis. This is an overview of the key data and derived interpretation in this study. First, we have the mineral log. Blue is dry weight calcite, and yellow is dry weight silica. Then we have the depth. We have the cylinder plot of the borehole radii from the acoustic borehole image with the acoustic image superimposed. We have the radii plot, that's the radius of the borehole. Then we have the static and the dynamic normalized acoustic borehole images. And the geological planes, the bedding and the fractures, they are represented by sinusoid when we have this unrolled image of the borehole wall. Then we have the track of the orientation. That's a tadpole track. We have the different features interpreted. The fractures are the green ones. That's the open fractures, and we have the red one. That's the bedding. We have the fracture density, the P21 fracture density in this case. The image segmented for WUGs. The blue is the WUGs or the WUGI fractures, and yellow is the matrix. And then we have the estimated WUG fraction. So the methods. First, about fracture density. So it's different ways. It's mainly 3 different types of fracture density. First, we have the P10. That's the frequency, basically. It's a number of fractures per meter along a sampling line. Then we have the P21 fracture density, which is the fracture trace length per area. And that's when you do the interpretation of partial sinusoids. You interpret only the part of the fracture which has the which is open. And the benefit of this is that you take into account small fractures with a low weight and large fractures with a higher weight. So that's why this is preferred in this study. You basically take the size of the fractures into account when you derive the fracture density. Then we have the P32 fracture density. That's fracture surface per volume. It's difficult to measure in the subsurface, but typically the P10 fracture density corrected for directional sampling bias is taken as the P32 fracture density. There are some issues related to the fracture density in borehole image data. And that's because the size of the wellbore is below the representative elementary volume of the fracture network. And what do I mean by that? Okay, if we look at an outcrop, this is a layer in an outcrop, and we zoom into this area, 10 by 10 meters. This is the fracture network, and an 8.5-inch borehole has this size as this little dot here. So from a single well, you cannot do a full representation of the fractures. You do not have a representative measurement of the fracture system within, for instance, a 1 meter thick layer. And typically, when you plot fracture density versus petrophysical parameter, you do not see any relationship at all. And in fact, I'm not sure if you can see it, but this is a density plot. So you have some colors down by the 0 line, and that's where most of the points plot. So in most cases, fracture density is 0 along a wellbore. And that's quite obvious when you have a look at this outcrop pattern. But what can we do then? So what we have done in this study is to plot the mean to 1 fracture density versus bins of different petrophysical properties. It's the dry weight silica in this case, and then you may get some more meaningful relationships between the different parameters. And then the WUG fraction, so that's the fraction of the borehole wall classified as affected by large pore. That's larger than the resolution of the acoustic borehole image. And this is basically a segmentation of the static image. And the threshold have been adjusted by intervals. So it's not a fixed threshold. It has been taken into the adjustment that has been done during the acquisition of the data, for instance. And then the quality control, Then the acoustic travel time image have been used to exclude areas that's not clearly associated to wellbore damage, and also to exclude damaged areas like washouts or borehole breakouts. There are some uncertainties in the interpretation of and the analysis of these data. First, the interpreter bias. So it has been basically 3 interpreters in the study, but we have done internal quality check. So we have tried to minimize this. Then we have the well coverage. So the data coverage is generally decreasing with structural depth. But within the Barra Velha Formation, the lowermost parts are lacking acoustic borehole image in 6 of 19 wells. So it's relatively good cover, but it's not the complete Barra Velha section included in all the wells. Then we have the data quality. We have used wells with even and relatively good quality, but some intervals are affected. And some intervals have reduced data quality, but less than 2% of the borehole image data have poor data, not usable for the interpretation. Then we have the well sampling, the issue with the representative elementary volume, as I mentioned in the previous slide. We have the resolution, so typically an acoustic borehole image log. It has much poorer resolution than we see in core, for instance. So typically the fracture density from core not typically, but the fracture density from core may be up to 10 times higher than what we see in the acoustic borehole image log. Then we have fractures versus bedding. Some intervals of the Barra Velha Formation has quite steep bedding, and in a few cases it's difficult to distinguish fractures from this bedding. And then we have the well distribution. So it's a few wells from different fields, and not all depositional environments are included. The wells tend to be distributed at highs and along ridges. So the basins in between these are not really included. Okay, then the different type of fractures. First, the low amplitude fractures. And this is the low amplitude of the acoustic signal. So these are dark sinusoidal anomalies. And these are likely to be open in the subsurface. And in this case, it's non-strata bound fractures. They cut through the bedding. Then we have vuggy fractures. That's patches of low amplitude, defining a sinusoid. And these are interpreted to be formed by dissolution along a fractured surface. Most of the fractures are interpreted as partial sinusoids. They are not going all around the circumference of the borehole image. See only parts, and these are interpreted as partial sinusoids, and that's quite important for how we calculate the fracture density. In general, it's quite a good match between open fractures that we see in the borehole image and what we see in the core photos. So the fractured intervals in the borehole image, they correspond to fracture intervals in the core. But it's not a one-to-one correlation. And that's caused by, first, resolution. fractures in the core is longer and more complex. It's more fractured, closely spaced than we typically see in the acoustic borehole image log. And in addition, we have some geometrical effects. The core slab or the core photo may have fractures with strike subparallel to the slab or the slab surface, and these may be missed out. Then we have the high amplitude fractures, and that's high amplitude of the acoustic signal, and these are bright in both static and dynamic image. Sometimes these are diffuse, and about 3% of all fractures are of this type. These are closed, maybe barriers, small-scale barriers, or baffled to fluid flows. And the interpretation is that these are deformation bands or minor faults with displacement smaller than we can see in the borehole image logs in many cases, and they typically occur in a porous and granular formation. They could also be veins in some cases. So this is a relatively diffuse high amplitude fracture, and this is the corresponding core photo. It's a bit squeezed, and it's a small. It's not an optimal depth shift in this case. If we zoom into the core, this interval, see first this silicified layer with minor fractures, but also this fault or deformation band, which possibly is cataclastic. Then we have the mixed fractures. They have mixed high and low amplitude. They are interpreted to be partly filled fractures. Sometimes these have kind of white, bright branches following the bedding, and it is a possibility that this pattern is caused by the hydrothermal silicification. This is an example of a quite wide mixed fracture. It's about 10 centimeter, and here we see the bright pattern going into the formation away from the main fracture surface. Faults are also observed. This is an example of a minor fault where we can match the bedding from one side to the other side of the fault surface. And we also have some larger scale faults where we cannot match the bedding across the fault surface. And these faults may be associated with high or low acoustic amplitude, or both in some cases. And some faults are suggested to be associated with silicification. This is a minor fault with an offset of about 10 centimeter. And we see a quite wide 5 to 10 centimeter high amplitude band, bright one, along the fracture or along the faults, and some of the layers in the vicinity also show high amplitude. You also see that the dry weight silica, the silica content picks up slightly in this interval. So the interpretation is that we have a silicification of the host rock due to a silica-rich fluid flowing along the fault and then into the layers. This is an example of strata-bound fractures. It's low amplitude fractures, and they are steep, stopping at the layer boundary here and here. And this is typical in layers with high dry weight silica, so silicified layers. Some major low amplitude fractures have also been observed. These have a very large apparent aperture, and we also see a response in the travel time image. These are interpreted to be due to dissolution along the fault or the fracture, and we can see these both in calcium and silica-rich intervals. So in this case, it's a limestone. It's high in calcium. Some major fault zones are also present. So first, we have an example where we have two main slip surfaces. This dark one, and this is surrounded by a fault damage zone. So it's a high fracture density in an interval of about 12 to 14 meters around this fault. We also see that the orientation of the fractures, the strike is similar to the strike of the faults. The faults are in black, and the associated fractures in the damage zone, they are in green. You see that this specific fault damage zone is in limestone rich or calcium rich lithology, low in silica. Here is another example, and in this case the interpretation is that we have dissolution enhanced fault planes. These are dipping about 60 to 70 degrees, and then this main fault zone or fault core is surrounded by an interval with high fracture density covering about 20 meters, or near 20 meters in this case. And also in this case, the fractures in the damage zone has the same strike as the faults, the main fault surfaces. Fractures are also related to karst. This is an interval with it's a very large some cavities or caverns along this or in this part of the well, and above that we see an interval with breccia and very high fracture density, and it's a very complex fracture pattern above these cavern-like features, and these are quite challenging to interpret. It's it's difficult to get some to get a detailed interpretation out of a proper breccia. But fracture density is high. And then the fracture orientation. So this is for the open fractures, the low amplitude, fuggy, and the mixed fractures. So the first plot, that is the strike of all fractures. See that the dominant direction is north-northeast. It's a large spread. Dip is quite steep. They are generally more than 80 degrees. But if we consider the major fractures, that's the full sinusoids, then the north-northeast strike is more dominant, and it's less spread in the azimuth. But also for this one, the dip is quite steep. And the steep dip that indicate that a large part of these low amplitude fractures are extensional fractures, joints. Fracture orientation is quite variable when you look at all the individual wells. So the north-northeast, west-southwest dominating direction is not present in all the wells. But typically you have 1 to 2 sets of fractures, and in some cases you have a much larger spread. So the local fracture orientation is not quite the same as the general one that we see when you look at all the data. Then we have the orientation of the in situ stress, and that's interpreted from the borehole breakout. The borehole breakout that typically occur in dense layers. And the borehole breakout are oriented in northwest, southeast direction. And that gives a maximum horizontal stress in perpendicular to this. And the data we get, or the average we get, is 51 degrees. And that's oblique to the main fracture orientation, and that support that the fractures are natural open fractures and generally not induced by the local stress in the vicinity of the well. Then the fracture density, it's a large variation between wells. So these are the 19 wells. It's about 2 orders of magnitudes variation in fracture density. And it's also variation between the fields. So these are colored by field. So we see that field C, for instance, has the highest fracture density, 2 wells, whereas field B, for instance, has relatively low fracture density. So what we think is that it's a structural control on the fracture density in addition to a facies and lithology control. Yes. And then we have fracture density versus excess permeability. So this is a plot of mean fracture density versus the well test permeability divided by the log-derived permeability. So if we start with field C, you see that the fracture density correlates quite well with the excess permeability. When the fracture density increased, the excess permeability also decreased. But that's not the case for all the wells. So for field B, for instance, that plots generally along this axis is quite a poor correlation between the 2 parameters. And the other fields, they plot generally in between these 2 main trends. So, but what we see is that the intervals with high fracture density, they show excess permeability. But also excess permeability is controlled by the depositional and diagenetic processes shown by these cluster of wells, where fracture density is generally low, but it's a significant excess permeability. So it's a combination. You have both. The fractures, they are not present all over the place. This is a summary plot. See that the fracture density, that's the green in this track. So it associates with high silica, both in the spectral log and in the multimin modeling. And also we see it's a high variation, in a very large variation in the bedding orientation. And that's the red tadpoles on this track. And finally, it's also high Vog fraction within this fractured interval. Then the P2 fracture density versus silica content. So this is the mean P21 fracture density. It's binned to avoid or to reduce the effect of the well bore being smaller than the representative elementary volume of the fracture system. We see it's a quite good correlation between the dry weight silica and the mean P21 fracture density. And similar when we use the petrophysical model, the multimin modeling, see mean P21 fracture density correlates very well with the volume of quartz. we also see a correlation between the mean fracture density and the bug fraction from borehole image logs. But when we look at one field, then the correlation between the mean fracture density and dry weight silica is less strong, and we think that is related to the fracture sampling area, and that's also related to the REV issue. And basically, you have too few data in some of the bins to have a proper representation. You don't have enough data to see any relationship, and that's in particular an issue when you look at only one well. So in these bins with dry weight silica above 15%, then you have very few data. So it's not that easy to get the proper correlation. You do not have representative data, basically. Then P21 fracture density versus porosity. First, we look at the high silica intervals. So this is the distribution. It's fracture density on the vertical axis again, and then we have the NMR porosity bins along the horizontal axis, and see that the highest fracture density is for the highest porosity, and we relate that to the dissolution, the association of dissolution and fractures. If we look at the low silica intervals, that's with dry weight silica less than 15%, then we first see it's a much lower fracture density in general. But also for this one, we have the highest fracture density for the highest porosity bin. You see low fracture density, typically in some depositional breccias and conglomerates, where we have poorly defined bedding, and also in some intervals, or in intervals with grainy or shrubby borehole image fascias. Okay, then the summary. First, fractures have been interpreted in the acoustic borehole image logs from 19 wells across the Santos Basin. And we have interpreted different types of fractures, and that's quite important to distinguish between open and closed fractures in particular. And we have also subdivided into low amplitude general fractures, buggy fractures. Here we see an example of high amplitude. We have the mixed fractures, and this is an example of a minor fault. We are focused on the potentially open fractures. Again, that's the low amplitude, the buggy fractures, and also the mixed fractures. And we also see that the fracture strike is dominantly north-northeast, south-southwest, and that is similar to the main fault orientation in the Santos Basin, reported in a few papers recently. The P21 fracture density for low amplitude fractures correlate with the volume of silica for both multimin and spectral logs, and also with the bug fraction from the borehole image segmentation. The fractures are also frequent in fault damage zones, and above and below cavities. And the fractures contribute to excess permeability, together with sedimentological and diagenetic features. Okay, more details can be found in this paper, published a couple of months ago in Journal of Structural Geology. So please take contact if you want a copy. And we would like to thank ANP for making the data available, and also Equinor for the approval of the presentation and the paper. And thank you for the attention. And I'm happy to answer any questions if we have time.
Thank you all. Yeah, we have a couple of minutes to the questions. We have some questions in the chat. Remembering that if you want to ask questions, you need to be subscribed in our channel. The first question we have is from Beatriz. Hi Ole, thanks for your presentation. How do you differentiate vug porosity from fracture porosity, and how do you quantify them?
Yeah, good question. We have not really done that. We have really not done that. That is too tedious. But the general assumption is that the fracture porosity is relatively low. So the main porosity is in the matrix in this case, and I think that fits well with the production experience from the area. But I do not expect any high volume of hydrocarbons in the fracture network. The volume of hydrocarbons would still be in the matrix, I believe, and that the reservoirs in the Barra Velha Formation is in some intervals type 3 fractured reservoirs of Nelson, according to the Nelson classification, where you have the main volume of the hydrocarbons in the matrix, but where the fractures increase the overall permeability of the system, but not that much the porosity.
Perfect, thank you. Another question is, what can be the impact on P21 logs when categorizing all the mentioned types of fractures as naturally open fractures?
It's can you repeat the question, please? I did not quite get it.
What can be the impact on P21 logs when categorizing all the mentioned types of fractures as naturally open fractures?
Yeah, if you also include for instance, the high amplitude fractures, then you will overestimate the P21 fracture density slightly. But I think also the high amplitude fractures, they typically occur in the more shrubby or grainy fascia. So you may add some artificial fracture density in the kind of the good fascias.
Okay.
But overall, if you look at a whole well, then it will have a minor impact. I think 3% of all the fractures are the high amplitude in the wells we looked at.
Okay, so it's not a huge overestimation.
It's not a huge overestimation, but it will impact the distribution. You may put in fractures in some intervals where you have good matrix and it produces very well anyway, and you, yeah.
That's great.
Yeah,
I have a question from myself. It is, I've been working with interpreting the NMR logs. I saw that you compared some of your fracture densities with the total porosity from NMR logs.
Yeah.
I recently published a paper in the SPWLA symposium last year, showing a method for interpreting the NMR logs when it is being impacted by vugular porosity, and I've seen this effect also in fracture porosities. My question is, have you seen the NMR logs? Like, have you seen any impacts of maybe mud invasion in fractures, mud invasion in bugs? And if you corrected for these effects, or we're just comparing just to have a broader view of the comparison?
Yeah, we have seen the similar effect in the wells we have studied. Yes, I don't remember all the details of that because it's other in the team that had focused mostly on that. But we have seen the same effect. But that's, I think, related basically to the major open fractures, where you also see an effect on the travel time image, a significant effect on the travel time image. And that's, I guess, that's in specifically when you look at the porosity bins in the NMR, you have some specific patterns. Yeah. So okay, I'll move to this slide. So I think you probably know more than me about that specific thing. But please correct me if I'm wrong, but I think that is mostly relevant for these type of fractures.
Yes,
so,
exactly.
Which has a really large apparent aperture, and you see the response, very clear response in the travel time image. And then exactly. I've not plotted the NMR in this specific case, but you have some characteristic pattern of the porosity bins in the NMR log. But I would be interesting to see your paper.
I can send it to you.
Thank you. Thanks.
The presentation. Thank you for your answer. We don't have any further questions, so I think we can wrap this up. I want to thank you in English first. It is a pleasure. It is always really nice to see. I think these are one of the prettiest image logs that I've seen in a while, and it is always good to see them because there's a lot of information that can be extracted from these logs. So thank you very much for the presentation.
Thank you very much for giving me the opportunity to present this study.
And sorry for the technical problems in the beginning, but we were able to solve everything very fast, so it was not a major issue. I'm going to change to Portuguese now. Pessoal, muito obrigado. Obrigado por participarem. Nós pedimos desculpa pelos problemas técnicos do início, mas foram resolvidos rapidamente. A gente, como eu falei, né, essa é a nossa terceira, nosso terceiro streaming, né? Então a gente ainda está aprendendo aí, né? Mas conseguimos resolver e a apresentação foi muito boa. Se eu não me engano, a gente consegue depois editar o vídeo para cortar aquela parte, mas também não tem problema. Queria agradecer a presença de vocês, relembrar também de se inscrever aqui no canal, né? Se puderem compartilhar o vídeo aí com colegas que tenham interesse na área, né? Claro, o vídeo vai ficar no nosso canal. E relembrar de seguir nossa página do LinkedIn e de se inscrever na associação, caso vocês não tiverem se inscrito ainda. E né, relembrar aí, no próximo mês teremos mais um webinar, né? E fiquem ligados aí na nossa página do LinkedIn e façam a inscrição para receber os avisos. Muito obrigado, pessoal, e até a próxima